Hello, my name is Claire Walsh. I'm from the Centre for Advanced Biomedical Imaging at University College London, and today I'm going to be talking about point spread function estimation and deconvolution for serial sectioning block-facing imaging. Serial sectioning block-facing imaging. Essentially what you have here is a sample embedded within a hard resin block. That sample is mounted within a system. The system contains an automated sectioning blade as well as some sort of microscope system. Now, as you can see on the right-hand side in the video, this automated sectioning blade takes very thin sections off the surface of the block. After each section, an image is taken with the microscope system. Another section is then taken, another image, and so on and so forth, acquiring a full volumetric stack. Now, crucially, these sections are vacuumed away. We're not interested in the sections themselves, we're interested only in the block-facing imaging. Another really important thing to remember about this type of imaging is that samples are stained before they are embedded. So by comparison to other serial sectioning techniques where you might take a section, stain it, and then image it, our samples are stained before they're embedded. The big advantage of this type of technique is that you get inherent alignment. So whereas with serial sectioning image-facing techniques where you cut the sample and then image the section, by imaging the block face, you get this inherent alignment and you remove what is a very challenging computational problem of realignment afterwards. So here, this is 3,800 images that required absolutely no post-processing to realign them. So the real downsides to this type of imaging are what we're calling a shine-through artefact. Now, if we take a look at the diagram here of the zoomed-in part of the sample, what you have is that you get incident light onto the block surface, and this excites whatever fluorophores you have on the surface, which you capture. That's great, those are the ones that you want. But in addition, some of this incident light is transmitted further into the block. And because the sample was pre-stained, any fluorophores that are just below the surface are likely also to be excited and will be captured in the image of the block surface. This is a problem, and the way it manifests itself is as you look here. So in the XY plane, you essentially get blurry out of focus structures before they come into focus a few slices later. And in the XZ, you get this kind of comet tail artifact. So the yellow boxes here just show stills with yellow arrows indicating the out of focus structures in the XY, and the comet tail artifact visible in the XZ. And really, the fundamental problem is that this leads to an inability to segment or a really poor segmentation result. So there are a few approaches that we could take to try and reduce this shine-through artifact. The first is physical, the way we prepare and image the samples, and the second is computational or post-processing approaches. So in terms of physical reduction in shine-through, we used an opacifying agent, by which I literally just mean a black powder. So here you can see some samples with increasing concentration of the black powder. We used a powder called Aerosol Black, which is a carbon-based powder widely used in the printing industry. And it has a specific transmission spectrum, so from 350 to 650 we have this very broad absorption, lack of a transmission, and then from 650 and above we have this sharp increase in transmission. And the way a pacifying agent works to minimize shine-through is simply that the light that's incident on the block face won't penetrate any depth into the block where there's an opacifying agent, so you won't excite any of the fluorophores that are below the surface of the block. And obviously there's a concentration dependence to this. So we wanted to have a look at this concentration dependence, and specifically we're very interested in quantifying this at this 650 to 700 nanometer range. So to do that we used standardized cell samples, so these are cells simply cultured in a 3D gel, and we stain the nuclei of these with a far red nuclear dye. So as you can see, the comparison in the XZ planes between the 32 and the 2 milligram per mil, you can see much less evidence of this comet tail artifact in the 32 mg per mil than you can in the 2 mg per mil. And we actually quantified this, so we looked at 10 ORIs in each of the 5 concentrations, and we fit monotonic exponential decay to those cases. So when you look at the fit parameters, so the second panel, the decay constant, you can see that you get a decreasing decay constant with increasing concentration. Notice that it's an increasing negative decay constant there, as you would expect. But also what we found very interestingly was that the 2 and 4 mg per mil have quite a similar initial intensity, and then there's this very steep drop-off at 8 and above. And when you look at the images back on the left-hand side, you can see this. It manifests itself as poor signal-to-noise ratio that you can see in the 32 mg per mil by comparison to the 2 mg per mil. In addition to this, we found that when we went to high concentrations, the 8 and above, we had inconsistencies with the resin setting. So this capped us to using a maximum concentration of 4 milligrams per mil, and it meant that whilst the physical sample prep obviously helped reduction in shine through, we were still going to need computational post-processing. The post-processing approach we took was a deconvolution, and to do this in classical deconvolution, I, so the image that you have, is equal to O, the object, convolved with H, the point spread function, and additive noise. So to retrieve the object that you want, you have to deconvolve your image I with your point spread function, and you need an estimation for the noise distribution. Now, estimating a point spread function is not a trivial matter, and there's a few ways you can do it. You can do a blind deconvolution that estimates both the point spread function and the object at the same time. You can empirically measure it using sub-resolution beads, or you can use a computational model to estimate it. Now, what I'm showing here are point spread functions achieved by a computational model with different refractive index mismatches. So for a computational model approach, you need a number of parameters of the imaging system as well as the sample. And whilst these models provide very effective estimates, the difficulty that we have is that because we have a serial sectioning block facing technique, we're not like other imaging systems. So in more standard imaging systems, you have contamination of the focal plane by light from both above and below. Because with serial section imaging, you're physically removing any sample above the imaging plane, you don't have this contribution anymore. So your point spread function is highly asymmetrical. You can think of it kind of like this in effect, where you cut off one half of your point spread function. And this means if we want to use this mathematical approach to estimating the point spread function, we need to alter these models slightly. Now, the approach that we ended up taking was based on the literature and used small structures within our image stacks to estimate parameters for the generation of a synthetic point spread function. The advantage of using point-like structures in the image stack is that you don't have to try and empirically measure a point spread function, which is practically very difficult to do, but you're still getting the benefit of having some empirical information there. Now, so the diagram shows the kind of the process that we go through. So you find one or several point-like sources in the image stack, you extract them, you do some denoising, and what we then did is we used maximum intensity projections in the X, Y, and the Z directions, and we fit these to either a Gaussian model, which is shown there, or we just extracted the full width half maximum. From that, you could then generate a symmetric point spread function using a simple model, and then we very simply just zeroed the lower half of that and removed the background. Now, these are some examples of 3 different point-like sources from our imaging stacks, 1, 2, and 3, and they differ in a few ways. So the biological structures, blood vessels, cytoplasm, and blood vessels again. Also, the wavelength that they're taken at differs, and this is important both for mathematical prediction of the point spread function and also because of our aerosol black transmission dependence. They also have different pixel sizes and different concentrations of aerosol black. And ultimately, all of that leads to 3 different full width half maximums for each of these samples. Now, in particular, we took samples 1 and 3 on for further processing. And I want you to just have a look at those images on the left-hand side and notice that in sample 1, you have what looks like a Gaussian point spread function. There's not very much evidence of lobes, side lobes, diffraction lobes on the small point-like structure. For number 3, however, there does seem to be, visibly, you can see that there are some sort of a diffraction pattern or these side lobes on the image. Because of this, we used 2 different point spread function models. So first, the left-hand side, the stack was taken from a tumour vasculature with the pixel size and aerosol black I've already mentioned. Now for this, because we didn't have a diffraction pattern evident, we chose a Gaussian model for the point spread function. By comparison, the healthy brain, it had a much smaller pixel size and a higher concentration of aerosol black. And as we said, the diffraction pattern was evident. And so for that, we chose a Gibson-Laney model. And here, these are just the original stack images. Before any deconvolution, you can see the tumour is a far, far poorer image stack to work with than the healthy brain. For our deconvolution, we chose a Richardson-Lucy algorithm. It's very widely used, iterative approach with a slow convergence. It has noise amplification at higher iterations, and because of this, one of the main issues around the Richardson-Lucy is how to choose the stopping criteria. So to begin with, we're going to look at the healthy brain sample. We have 3 panels here for the original 50 iterations and 100 iterations. On the left-hand side of each panel, you have the segmentation, and on the right-hand side, you have maximum intensity projections in the X, Y, and the XZ planes. And just from visual inspection, it would appear that 50 iterations is the optimum. There's the least amount of stripe artifact and noise, and the segmentation looks by eye to be good. But we further wanted to quantify this. So in this panel here, what you can see is that 0, 20, 35, 50, and 100 iterations. And we looked at the orthogonality of selected vessels. So if you just look at the top row, I'll explain what we did. We looked through the vessel stacks to find 6 vessels that were all running approximately parallel to the imaging plane. What we did is we selected ROIs around these vessels, and we took a profile normal to the vessel direction. So you can see on the top panel on the left-hand side, that red line is the line profile. So the top row in each of these graphs is the XY line profile at each of these iterations. We then took a slice Z stack in this normal along this normal line to the vessel, and we took the line profile in the Z normal direction. And so there you can see along the bottom panel you have the Z direction line profiles. Now from these line profiles you can derive a vessel diameter, and if you take the ratio of the XY diameters to the Z diameters, you get this orthogonality measurement. And we can see here that initially it starts off not very orthogonal. By 20 iterations we're already orthogonal within the errors, and it continues to be so up until 100. So this is a good indication that 20 is probably a good iteration number. In addition to that, we looked at the signal-to-noise ratio via line profiles. We also quantified the contrast to noise and as well the number of vessel segments in the segmentations. So you can see here 20 is the beginning of this minima in the number of vessel segments. And it's not the peak of the contrast to noise, but it is an increase in contrast to noise from the original. For the vessel diameter distributions, again from the segmentations, you can see that 20 is at a peak in terms of the median vessel diameter. And all of these are good indications that 20 is the correct iteration. So next we're going to look at the tumour, and in this case we did the original 35 and 100 with the same images as previously. We also took similar measurements. I mean, visually, with the tumour initially, it's much easier to see that 35 iterations visually appears to be far better than the original, obviously, but also 100, there is a lot of noise that you can see. And that's evident when you look in the line profiles. So what we did is we actually only looked at the orthogonality in 35 to see if we'd hit our initial orthogonality criteria. So we looked at 4 different vessels, and you can see that actually we haven't quite hit the orthogonality measure apart from in that last vessel 4. We also looked at the same metrics of vessel diameter distribution, number of vessels, and contrast to noise. So we appeared to be at the peak for the contrast to noise. The vessel segments is right in the middle of the two. And with our vessel diameters, we're again at this peak of the median in those that we tried. But I would say from overall from these, the fact that we haven't quite reached orthogonality yet suggests that we should go to more iterations than 35, but 100 is clearly too many. But what the take-home message from both of these two is that we have really achieved a pretty effective deconvolution from the samples. So just to conclude now, we've shown that serial sectioning block-facing imaging suffers from this subsurface fluorescence shine-through that reduces the axial resolution. We looked at both physical and post-processing methods to reduce this. The physical method of opacifying agents works, but it wasn't sufficient on its own. We actually required a deconvolution, and for that we needed a point spread function estimate. We estimated this point spread function using small structures from within the image stack. We used these small structures to fit a standard PSF model, and finally we altered this synthetic model by zeroing the lower half of it. So these half PSFs that we produced were used in the standard deconvolution algorithm, the Richardson-Lucy, and produced effective deconvolutions. By quantifying some measurements on the image stacks and the segmentations, we were able to get an objective criteria for how to optimize the number of iterations. Finally, I'd just like to acknowledge my co-authors, Natalie, Simon and Becky, and also to thank my funders. Thank you very much.